Okay, we're going to go ahead and finish up chapter 5 here with our complex zeros. If you remember, complex numbers are the numbers that have the I involved. Some people call it the imaginary part. It's not imaginary, of course. These complex numbers are used all over the place in physics and engineering. So, the fundamental theorem of algebra. If f of x is a polynomial function of degree n, where n is strictly positive, then f has at least one zero in the set of complex numbers. And this sort of illustrates that a little bit. What's the most important part is basically an nth degree polynomial has n zeros. Now that could mean that some of those zeros are repeated, so maybe 3 is a zero and it's actually x minus 3 to the 5th power, so it has a multiplicity of 5 in that case. Each of those would be counted individually as 5 separate zeros. Getting into more of the stuff that's going to be in your homework. So I want to show you different ways to factor as we're going through this. We're going to factor over the set of complex numbers. This is a quadratic-like expression and factors quite nicely, but then when I want to continue factoring it, that's a difference of squares, and so we end up with radical 5. This is a difference of squares. If you make that x squared minus 4, then when you take the square root, you get plus or minus 2i. And in general, we have this rule here. Now, if we factor just over the set of rational numbers, then we have to get to here. Because rational numbers are a subset of the real numbers, which don't include I and things like that, or radicals. Now, if we want to do it over the real numbers, then we can continue with the radicals, but we're specifically saying not the complex numbers. So we can't break into the I component of it. And just quickly to show you where this comes from, it can get broken up like this. Part 2. If f has a real coefficient and a plus bi is a 0, then its conjugate a minus bi is also a 0. This was sort of like the previous talk that we just had when we had the irrational answers. If we have an irrational, then both conjugates are going to be zeros as well. Similar proof, actually. So here we have, we want to come up with a polynomial in factored form. Well, 0, that's easy enough, because these are zeros, following zeros. Remember, it's always the opposite sign, x minus 3, x plus 7. So that one was fairly simple. And when we get to one that's more complicated, if 3 plus I is a factor, or is a 0, then we know that 3 minus I is also going to be a 0. So both of these are going to be zeros. Similarly, from the theorem we had in the previous talk, if 7 minus root 2 is a 0, then 7 plus root 2 must also be a 0. Its conjugate must be a 0 also. So for number 3, given that negative 3 is a 0 of this function here, find the other zeros. Well, if it's a 0, then when we do synthetic division, we should get a remainder of 0, which we do. And you'll notice it's going to drop from a 4th degree down to a 1x cubed, 3x squared, plus x plus 3. And once again, you could continue on trying to come up with other zeros. So we have plus or minus 1, plus or minus 3, plus or minus 9 if we from the previous talk. But I noticed that this actually factors by grouping quite nicely. So we end up here. Now, this is going to be a rational, real solution. This one's going to be a more complex, meaning plus or minus the square root of negative 1, which is plus or minus I. So here's our actual factors, and here are zeros. Now, what this tells us is that because it's a 4th power, that there's going to be 2 of these. So we have a multiplicity here. Because all the degrees have to add up. So 1, 2, 3, 4 have to add up to our exponent here. Our 4th example says just given 2 plus I is a 0, that means we know right away 2 minus I is also going to be a factor. So since we know that these two are zeros, I can FOIL it all together, and I end up here. And you'll notice this is a difference of squares. X minus 2 is the first part, and then I is here. A little quicker way of multiplying that together. Now that I know that these the factors of this are zeros, which we already know what those are, when I divide this out by that, notice I got 0 as a remainder, and here's my quotient. So the factors of this equal to 0 are going to be zeros, and the factors of this equal to 0 are also zeros. I already know what these ones are. These ones are here. So this one, I apply the quadratic formula. You can look through the details of that. And I end up with negative 3 plus or minus root 2. So again, I'm going to leave this to you to come up with the work and to double check that and everything. Number 5, we're going to find all the zeros of this polynomial function. And by the way, all real numbers are also complex numbers, so even if we don't end up with an I, every number that you can even imagine with the I or without the I is called a complex number, because the real numbers are just a subset of the complex numbers. So here are all of my potentials of finding the zeros as directions. Again, I broke the 9 up. Its factors are 1, 3, and 9, and the 3 is 1 and 3, and I wrote them out. And remember, there aren't 4 potential, there are 8, right? It's plus or minus, it's double. So we might end up with a multiplicity. So I did 1, I did negative 1. When I say did, I mean did synthetic division. I didn't get a 0 remainder. However, when I got to plus or minus 1/3, didn't get 0 remainder. When I did positive 3, I did get a 0 remainder, which means this third degree polynomial drops down to a second degree polynomial. And these are easy to figure out because we can either factor it, which we can in this case, and if it's not factorable, we just use the quadratic formula. So here are the zeros. It looks like we have 3 twice, and then we have 1/3. Oh, I guess I lied when I said I did 1/3. I didn't actually do it. But you can see we have a multiplicity here. For this one, here we have a 4th degree, and the only potential rational ones, it's very nice, there's only 4 potentials. And I tried positive 1, didn't work. I tried negative 1, it did work. It dropped it down from a 4th degree to a 3rd degree. So this is now x cubed minus 9x squared plus 19x plus 5. I'm not going to keep going with my synthetic division. And I tried 5, and it ended up being a multiple as well. So this means that x plus 1, x minus 5 are 2 factors, and negative 1 and x equals 5 are zeros of this function. I've now dropped down to a quadratic, which all I need to do is the quadratic formula, and I get 2 irrational numbers. So you can see 4 numbers for zeros. That's a lot of information.